Okay, hello everyone. Welcome back to a new tutorial. This time we're going to talk about the beam deflection. So let's take a look at the overall things that we're going to go over tonight. Definition of deflection in beams. Then we're going to talk about the factors affecting deflections in beams. Then we're going to go over examples of deflection formula. I'm going to discuss some theory behind deflection calculation in beams. Then we're going to do example 1, then example 2, and we'll have a special case we're going to discuss that doesn't apply, of course, to example 1 and 2, and we're going to do an example on that special case. So let's get started. So the question is, what is a structural deflection? The deformations or movements of a structure and its components, such as beams and trusses, from their original position. Okay, enough said. Let's take a look at the picture here. So in the first figure, or the beam above, we have the beam unloaded, and we see the neutral axis is the horizontal line, leveled. Then when we apply a force F to the middle of the beam, we see the neutral axis bending or taking this shape, and this is just to show you the difference between the neutral axis before loading and after loading. So this is the first example we talked about. So what is the deflection then? If we take a look at the just middle, or if we take just half of the beam and we look at the distance between the neutral axis before the beam is loaded and the neutral axis, the location of the neutral axis after the loading, this is the delta, or the deflection. In our case, this is the maximum distance we can get, because I'm taking the deflection at the midspan. This is another example. It's a cantilever beam. So we have a cantilever beam fixed to the wall, for example, right here, and it's loaded by a point load or a concentrated load at the free end. So it will deflect something like this, and this distance between the original neutral axis and this neutral axis is the delta max. So what are the factors affecting the beam deflection? A loaded beam deflects by an amount that depends on several factors, including, just let's take a look at them one by one. The magnitude and type of loading. Of course, the higher the magnitude of the load, the more deflection you're gonna expect. And the type of loading here is the loading uniform, or is it concentrated? That of course changes the way we talk about deflection, or the magnitude or the amount of deflection. The span of the beam. Again, compare two beams. One is 10 feet long, the other is 20 feet long. If we apply the same loading, of course you're going to expect the 20 feet long beam to deflect more. The material properties of the beam. Modulus of elasticity. Is it a concrete beam? Is it steel beam? Is it timber? So the type of material will play a huge factor in determination of the deflection. The properties of the shape of the beam, the cross section, mainly the cross section of the beam. Is it a deep beam? Is it just a T beam, a rectangular beam? Of course, all of these factors play a role in the magnitude or the amount of deflection that will take place in the beam. And the beam type. Simple beam will deflect differently from a cantilever beam, from an overhanging beam, or a continuous beam. So let's take a look at a typical deflection equation. Here is a simply supported beam with a uniform load W, and the delta max that takes place at the midspan is calculated from this equation. Okay, let's take a look at all the things that go inside this equation. First, we have the load W. Remember we said that the magnitude of delta depends on the load, as we mentioned above. Second is the span, that's the L. Material properties is the E, or the modulus of elasticity. And finally the shape properties, which is the moment of inertia, or the I. Let's take a look at examples of deflection formula. Okay, this is simply supported beam. Delta max at center or at midspan is 5W L to the 4 384 EI, and if you want just to find the deflection of the beam at any distance x from left to the right, not necessarily the midspan, you apply the second equation. This is the simply supported beam with a concentrated load at the midspan. Again, delta mass at point of load. So whenever you move the load left or to the right, always the deflection is going to be below the or at the point of load. And delta x is when x less than L over 2 is this equation. Okay, the third example is the cantilever beam. We have the P acting at the free end, and delta max at free end, of course, is PL cubed over 3EI, and delta x, taking x from left to right, is calculated using this equation. All of these equations, you're going to see the load, W or P, you'll have a length, L, you have an E, that's the material properties, and you have an I, that's the cross section. Okay, our goal tonight is to get the expressions I just mentioned. Here is some theory. External loads cause beams to deflect. The shape of the deflected beam is defined by a function y of x. The deflected shape is called the elastic curve. What I'm talking about? Okay, assume that between point O and this point we have a beam, and the red curve here represents the deflected shape of the beam. If I use this coordinate system, this is the y and this is the x, I can express this y of x as it says. It's a function of the y as a function of the x. The goal here is to get an equation for this line. If I get an equation of this line, I can get the value of any point along the line. How can we do this? Let's see. Based on the moment shear load relations and the beam curvature, the governing differential equation for deflection of an elastic beam is, and again, this you can get from your mechanics of material book or structural analysis book. I don't want to go through a lot of theory here on how to derive it. My goal here is just to show you examples and how can you use whatever we know right now or to find the equation for the deflection or the deflected shape. This is the governing differential equation. It says here that the second derivative of the function y of x with respect to x equals to the moment equation divided by EI, and EI is known as the flexural rigidity. Okay, that's the equation again. So this equation obtained is a second order linear differential equation. In this case, if we integrate that equation twice, we will get an expression for y of x. It's as simple as this. Okay, let's see. Now I'm gonna move the EI, assuming I'm using a beam that's made of one material only, and I'm assuming that the cross-section properties of the beam do not change along the beam. So what I'm saying here, I'm gonna move the EI to the other side and integrate once the mx. So I'm integrating mx. I'm gonna get a constant of integration C1. Okay, but remember this. Looking at this figure right here, if I want to see dy dx, it's basically you can think of it as y over x. So what is y over x? Y over x is the tangent of this angle theta, and for small angle the tangent of the angle is the angle. Okay, and that is what we called the slope at this location. So I can rewrite the above as this. Anyways, I'm gonna continue integrating. Remember, I'm gonna integrate twice. So after integrating twice, I'm gonna end up having this equation right here. You can see we have a C1 and C2 now. Okay, now our job is to find the C1 and C2 values. For now, the constants C1 and C2 are determined from boundary conditions, or more precisely from conditions imposed on the beam by its supports. How so? Okay, now I have an equation right here, and EI is constant, so I don't worry about this. So it's an equation about y, which is the deflection. That represents the deflection. Okay, the deflection at point A is 0, and the deflection at point B is 0. See, the supports are not moving up and down, and we have deflections along the beam except for A and B. So if I integrate, I'm gonna end up having some kind of equation here, plus C1 x plus C2. If I can use these boundary conditions, I can solve for C1 and C2. Remember, the number of boundary conditions is equal to the number of unknowns. So if you have two constants of integration, you need two boundary conditions. Let's take a look at another boundary condition. Okay, again, there is not much difference about boundary conditions here, but we can see that the deflection at point A is 0 and the deflection at point B is 0. The interesting one is this one. At A, we have, of course, it's fixed, a deflection that's equals to 0, and the rotation or the slope is 0. Let's take a look at example 1. The cantilever beam AB is of a uniform cross-section and carries a load P at its free end. The free end is A, right here. Determine the equation of the elastic curve and the deflection and slope at A. So, two things we need to determine. One is the equation of the elastic curve. Then, from that, we need to calculate the deflection and the slope at point A. Here are the steps. Establish the x and y axis. We need to define which way is our x and which way is our y. This is the way I like to do that. Find the bending moment equation that describes the bending moment for the entire section of interest. The section of interest is the whole beam. So if I can find an equation that describes the bending moment for the whole beam, I'm done. Okay, how do I do this? I cut the beam to analyze it. I'm taking section C. It looks like this. These are the internal forces. Now find the bending moment equation. I need the equation for this moment. How do I do this? I take the sum of moments about C. Summation of moments about point C equals to 0. So M plus P times X, rotating this way, and that should equals to 0. From that I can say that M equals minus Px. Substituting in the elastic curve differential equation, remember EI second derivative equals mx. So EI second derivative equals minus Px. That's the one we got a moment ago. Integrating, now I'm going to integrate it twice. This is the first integration. Minus 1/2 Px squared plus C1. I can continue integrating, or I can apply the first boundary condition. It's up to you. The way I did it for this example, I applied the boundary condition directly after the first integration. What is my boundary condition? Looking at this beam at point B or at distance L, I have two boundary conditions. I have a boundary condition for theta and I have a boundary condition for y. But be careful. This equation right here is the equation that can help me get the slope. So I'm going to use the slope boundary condition. So at x equals L, theta equals 0. I'm going to use this. So I'm going to substitute 0, which is the theta, which is dy over dx, equals, and I'm going to substitute for x, I'm going to substitute L for x, then I can solve for C1. I get C1 equals 1/2 PL square. Now, my slope equation is EI dy over dx equals minus 1/2 px squared plus 1/2 PL squared. Integrating for the second time now so I can get the deflection equation. EIY equals 1/6 this, and now I have a new constant of integration, C2. Now applying the boundary condition at x equals L, since I'm talking about deflection, I look at the deflection boundary condition, y equals to 0. So 0 equals this, and then when I solve for C2, C2 equals minus 1/3 PL cubed. Now our deflection equation is EIY, this, and I substituted minus 1/3 PL cubed for C2. In a simpler form, this is the deflection. To find the slope and deflection of the beam at point A, we substitute x equals 0 in the appropriate equations. Why x equals 0? Because we've taken the, remember, point A is at the left of the beam, at the free end, and we started our x and y axis, the origin was at this free end. That's why x equals to 0. So if I substituted into the theta equation for x equals 0, I'll have theta A will equal PL squared over 2EI, and if I substituted in the y equation x equals to 0, YA equals minus PL cubed over 3EI. So this is our final answer. Now I have an equation for the slope and for the deflection at the free end. From before, we had this figure, remember, and we have delta max at free end PL cubed divided by 3EI, which is identical to this one except for the minus sign. But here the minus sign just represents the deflection to be downwards. That's all. Now let's take a look at example number 2. The simply supported beam shown in the figure carries a uniformly distributed load W per unit length. We need to determine the equation of the elastic curve and the maximum deflection of the beam. The solution: first we need to establish the x and y axes. Here are the x and y axes. Solve for the reaction. This is a simply supported beam with a uniformly distributed load. It's very easy to find the reactions. What we need to do is just concentrate the load and divide it by 2. Concentrate the load, divide by 2. We'll end up having RA equals 1/2 WL, and of course RB is going to be equal to RA, which is 1/2 WL. But we will see that we don't need RB, we are going to use RA. Okay, find the bending moment equation that describes the bending moment for the entire section of interest. Cut the section in the beam to analyze. This is the cut. So now from this section we need to find an equation for M. How do we do this? We take the summation of the moments about D. It's going to be M, then RA multiplied by X, and that's going to rotate clockwise, so it's a negative. Then WX, we concentrate this segment of the load, and it's acting at the distance x over 2, so it's wx multiplied by x over 2, and that's a positive because it's counterclockwise, and that we should set this equals to 0. Now what I do, we put, instead of RA, we're going to substitute 1/2 WL, and then move everything except the M, or move the M to the other direction, it's up to you. We need to solve for M, and M is going to be 1/2 WLX minus 1/2 WX squared. Now we substitute the moment equation we got into the differential equation, and we start integrating. Integrate once, we get EI dy over dx equals to this expression plus C1, the first constant, and we integrate again to get the deflection. We're going to get this plus C1x plus C2. C2 now is the second constant of integration. What are the boundary conditions? The boundary conditions we have for a simply supported beam, like the one shown in the figure, that the at x equals 0, y equals 0, or no displacement or deflection at A. And for x equals L, it's the same thing, no displacement or deflection at B. So these are the boundary conditions. We will use, of course, if we are talking about the boundary conditions using the deflection, we're going to use the deflection equation. At x equals 0, y equals 0. So using this equation, EI, y equals 0, we put a 0 here, and if x equals 0, that term goes away, this term goes away, this term goes away, so we end up having C2 equals to 0. Now, the second boundary condition, at x equals to L, y equals to 0. So we said 0 equals, and we remove every single x and we put L instead. We'll end up having this expression. If we solve for C1, it's going to be minus 1 over 24 W L to the 3, or to the third power. Now we have a deflection equation. EIY equals this, and so y is W over 24 EI multiplied by this expression. The maximum deflection. For a simply supported beam with a uniform distributed load, the deflection is at the midspan at L equals 2. So all I need to do is substitute L over 2 into this equation. So I take away every single x and I put L over 2. I'll end up having YC, which is the point C is the point at midspan, equals to that simplification. We'll get minus 5W L to the 4 384 EI. From before, we had this figure, and delta max at center, it's 5W L to the 4 384 EI. So if we follow these steps, these problems become easy, but be careful with the integration and how to use the boundary conditions. Now the special case, and we need to pay attention to this one. In each of the two examples we've done, only one free body diagram, or only one cut, was required to determine the bending moment equation in the entire beam. As a result, a single function of x was used to represent M throughout the beam. Concentrated loads, reactions at supports, or discontinuities in distributed loads will make it necessary to divide the beam into several portions and to represent the bending moment by a different function mx in each of these portions of the beam. In short, if you cannot express the bending moment of the entire beam with one equation, you need to divide the beam into segments where each segment's bending moment is representable by one equation. So, examples. These are two examples right here. For example, from point A to point C, we will have an equation for the moment that is different from the equation of the moment between C and B. Same thing applies to this beam. So, what to do? Here is an example. For the beam shown in the figure, Determine the slope and deflection at point D. The solution. Looking at the beam and the loading, we can tell that the bending moment cannot be described by one equation, but segments AD and DB can be described by two different bending moment equations. The plan: obtaining an equation of the bending moment for the two segments, so we need to make two cuts. Integrating the differential equation twice for both, so it's just basically like doing the first problem twice, or the first two examples twice. Then we'll use the boundary conditions to find the constants of integrations. Then we will obtain the elastic curve equation yx for both segments. Okay, the first segment is going to be between, we're going to take a cut between A and D, so x is less or equal to L over 4. We draw the free body diagram. That's the free body diagram. Then we'll try to calculate M1. Okay, so I skipped the steps where you can find the reactions. I mean, by now it should be easy for you guys to do. So if I take the summation of the moments about E, I'm gonna end up having M1 equals 3p over 4x. That's the equation. This is the differential equation, remember, and I set it equal to 3 over 4 px, which is the equation of the moment for the first segment AD. And notice here that y1 is the function which defines the elastic curve of portion AD, because we're going to have two functions, one from A to D and the second from D to B. Now we integrate it twice. We're going to end up having two constants of integration, C1 and C2, and these are the equations. This is the equation for the slope, and this is the equation for the deflection for the first segment. Now let's try to do the second segment where x is greater than L over 4. We now draw the free body diagram. This is the free body diagram, and if I want to find the M2, I take the moments about point E. It's going to be M2 minus P, or minus 3 over 4P times X, then plus P times X minus 1/4 L, and this is the distance. So M2, I'm going to end up having M2 equals this expression. Okay, simplifying the expression one more time, simplifying it again. Now this is the equation I'm going to use in my differential equation. So this is my differential equation, and again y2 is the function which defines the elastic curve for the portion DB of the beam. Integrating an x twice, now I'm introducing C3 and C4. I don't want to confuse you guys, just be consistent. For the first portion we used C1 and C2. Since I'm having different concepts of integration for the second segment, I'm going to use C3 and C4. So from the equations, this is a summary of all the equations we have so far. This is the equation where we have C1, this is where we have C1 and C2, this is where we have C3, and this is where we have C3 and C4. So I'm having 4 constants of integration. And remember, in order for you to find the constants of integrations, you need boundary conditions, and the number of boundary conditions should equal to the number of constants of integration. Okay, so we need 4 boundary conditions. The question is, do we have them? Let's take a look. This is the beam. First boundary condition is at x equals 0, right here, y1 equals to 0. At x equals 2, or at x equals L, y2 equals to 0. Okay, so these are the only two I know. But what happens at point D? At point D, which is x equals 1 over 4L, the slope from the first equation should equal to the slope from the second equation. Why? Because it's a continuous line. And at the same point D, the deflection at point D, either you calculate it from this equation or calculate it from the other equation, supposed to be the same. So now I have 4 boundary conditions. Applying boundary conditions. At x equals 0, y1 equals to 0. So we look for the y1 equation, and if we substitute x equals 0 in this equation, we'll end up having 0 equals to c2 or c2 equals to 0. At x equals L, y2 equals 0. So we look for the y2 equation and we substitute L, and we'll end up having, and of course on the other side we substitute 0, so we will end up having this expression. Now at x equals L over 4, we have 2 equations that are equal to each other, theta 1 and theta 2, which are equations 1 and 3. If you look back at the like a minute ago, I listed all the equations for you. So we set these 2 equations equal to each other, and we at the same time substitute L over 2 for x. So we have this, and if it's basically the same thing, this is what I get. I cannot simplify it more. And the same way for L over 4, y1 equals y2, using equations 2 and 4, I set them equal to each other, and this is what I get. Now we have the following equations. We have this equation, 1, 2, 3, 4 equations, and they have C1, C2, C3, and C4. So 4 equations and 4 unknowns. So solving these equations, and this is the hard part, guys. And if you can solve these equations simultaneously, you will end up having C1 equals to this value, C2 equals to this value, C3 equals to this value, and C4 equals to this value. Okay, so these are the equations we had before with the C1, C2, and so on, and these are the results we got from solving these equations. So theta 1 now equals theta 1, which is from equation number 1. We move the EI to the other side, and we have this. And for y1, which is equation 2, after substituting the constant, and theta 2 is this, and y2 is this. So now I have the equation, theta 1 and y1. These are the equations for segment AD, the slope and the deflection, and for segment DB, the slope and the deflection. Now to find the slope and deflection at point D, use any slope equation, theta 1 or theta 2, to find the slope, and use any deflection equation, y1 or y2, because remember the deflection, and this was one of the boundary conditions, the deflection theta 1 equal the slope theta 1 equals the slope theta 2 at point D, and the deflection y1 equals the deflection y2 at the point D. So for simplicity, let's use the smaller equations. So if I substitute x equals L over 4, theta D is this, and if I substitute L over 4, I'll have y at point D is this. I know this tutorial is a little bit dense, and you need to, I believe you need to just pause in some of the parts and try to do it yourself. Try to integrate, try to solve the equations simultaneously, and hopefully you're gonna get the grasp of the topic. I mean, it's not that complicated. It's tedious, it's a lot of work, but this is the basic idea behind it. And that's it for now, and hope you learned something today. Thank you.